My name is Grzegorz, I come from Warsaw, I have a blog, and I will be working for Hazelcast since next month. And the rest is implementation details, so let's go straight to the subject. So, Java and functional programming and immutability, they have a long and interesting and twisted relationship. I remember a long time ago when Mark Reinhold would go on stage in Java 1 and say publicly that Java will never have lambda expressions because that would clutter the language too much. But as you can see, it changed a lot over time. And some of the mean people out there can actually say that after seeing one of the JFuture talk by Brian Getz or Mark Reinhold, they see that the language itself is borrowing more and more ideas from other languages like Kotlin and Scala. One of the ideas that it started borrowing more and more is immutability, which became kind of the hot thing in Java after many years. Java used to be purely OOP, but we figured out that immutability actually brings a lot of cool properties. And immutability for a very long time was sold as one of the missing pieces that would help Java grow further. But it turns out that implementing immutability is very difficult. And this is what we'll be speaking about today. So no functional frameworks, but we'll dive into the design and thought process and trade-offs involved when it comes to implementing immutable data structures in Java and in any other language out there. Because there are a few common challenges that needs to be overcome. But let's start with a quick quiz. So I prepared a very simple method signature. As you can see, it has a name, it has a return type, it has a parameter, and well, it returns a list of strings. It accepts a list of strings, and it's called transform. And I bet that only by seeing the method you have certain intuition about what it is actually doing. And this is where my question comes from. Can you tell me, what's the method doing? Just making the deduction based on the what you see on the screen. Any ideas out there? I've heard someone said something, but I didn't really hear it. But of course, that's one of the possible right answers. But I'm sure you are very anxious to see what the actual implementation is. So I won't keep you waiting. I'll just show you. So that's what I implemented. As you can see, it turns out that first we take the input list and we add some element taken from some internal state of this class. Then we add some constant into it. We order a pizza, and if there is a right lunar phase, we remove some elements. Then we add even more elements. We add those elements from this list to some other shared object, and then we mutate some static field, and finally we return the element. So I hope you didn't expect that. The thing is that if you adopt immutability and functional programming and qualities like refresh and transparency, it kind of reduces the potential error space and potential of the space for surprises in your code. So if you would be working in a language that adopted immutability as refresh and transparency, for example, like Haskell, you could have your intuition, your feel of potential weird stuff that could be happening inside would be really, really narrow. And really, when we actually interact with our programs, when we craft our abstractions, when we debug things, we need to generalize. We can never actually dig down inside to the assembly level or just reading raw bytes to see if everything was produced correctly. If you browse your source code, if you look at abstractions, at some point you need to stop digging down deep. And if you adopt immutability and other tools like this, this actually helps you craft tools that are more predictable and less buggy over time. Because if you can't mutate things, it turns out that there are less moving parts, and if there are less moving parts, the fewer things can break. So immutability is really great when it comes to minimizing the number of invalid states for your applications. But immutability at the same time enables very interesting optimizations that can be done internally. So for example, if you have an object that doesn't really change over time, such object can be actually memoized or just safely cached and reused all over the place, just like the number 17. So if you add a number, if you add 1 to the number 17, the 17 never changes. You derive a new value from your number, but the original can be shared all over the place. By the way, it works not only with the number 17. The same applies to properties of objects. So imagine you create a list of 147 elements, and guess what? If it's immutable, it doesn't change over time, which means the size or the hash code can be pre-computed and stored inside an object, which means that if you actually want to access those properties, there are no additional computations needed. Actually, if you have immutable collections, you don't really need to invest time into a very complex, so something based on array list or linked list. You don't need that infrastructure, because if your list has 2 elements, you know that won't change over time, which means that effectively you could implement an immutable list of 2 elements as a list that has, well, just 2 fields inside. And this is what happened with JDK9 and immutable data structures that arrived there. If you have a look at the list of 1 or 2 elements, that's indeed just a class containing 2 fields. So as you can see, immutability brings you like quite a lot of cool things, but it also brings a lot of additional complexity involved. But before we go deeper into that, let's revise what does it actually mean for an object to be immutable, at least in the Java space. So, according to Brian Getz from Java Concurrency in Practice, objects are immutable when their state cannot be modified after construction, when all their fields are final, and when the this reference doesn't escape during the construction phase. So, I have then a quick question for you. If we know that this is what constitutes an immutable object in Java, is string an immutable object? What do you think? Is string immutable? I see some. Is string not immutable? Okay, there are some people raising hands. Okay, let's calibrate the room to make sure that we are making deductions on the right data. Who is in the room at the moment? Okay, again, how many of you think that string is immutable? Okay, now we can properly reason about our data. So, if you have a look at the internal implementation of the string, well, you have 3 fields internally. One of them is private final byte array, private final byte coder, so far so good, but private int hash. Whoa, it turns out that hash field is not final, and it actually changes over time. Because if you create a empty string instance, it will start with the hash code of 0. And if you actually call the hash code method, it will get overwritten over there. So when it comes to the string class, not all of its fields are final, and its state actually gets modified after construction. So what do you think? Did they lie to us? Is string immutable or not? So as Nicola taught you a few hours ago, it actually depends. Because if you have a look at if you want to get an absolute answer, you will see that true immutability doesn't really exist. Because at the end of the day, all your models are being run by mutable and impure machines. So true eternal immutability doesn't exist, but immutability still can be respected at certain abstractions levels. So if you have a look at the string class, from your perspective as a consumer of that API, it will actually behave like an immutable class. although internally it will contain moving parts and will have non-final fields that might change over time. And this is okay because this internal state doesn't really leak out anywhere. Or does it? So it turns out that there are actual corner cases when those internal implementation details of potentially immutable data classes can actually leak out. But before we have a look at them, remember that at the end of the day, nothing really is immutable. Because at the end of the day, you can do a lot of really evil things that actually can violate any abstraction layer. So if we have mutable parts in our data structures, in our immutable classes, it means that actually immutable objects doesn't need to be thread safe. And thread safety is one of the most important arguments, most important selling points of immutable data structures. And some of you might say that, well, if this implementation does really have a concurrency bug inside, it shouldn't be really called immutable. And I would agree with that. But the point is, you need to remember that if our immutable objects are actually mutable inside, it can be very easy prone to concurrency issues. And this was the case with one of the Scala releases. I don't remember if it was 2.11 or later, but if you created a new list, empty list, or if you created a new vector, it could be observed by other threads as mutable in invalid state. So as you can see, immutability becomes a bit more complex if you start taking all of that into considerations. So once we know all of that, once we know that immutability needs to be respected only at the one abstraction layer at a time, let's try to think what does it mean to actually design a proper, good immutable APIs. Let's see a bad example first. For example, Java util list interface. So the list interface, or the Java util collection interface, it contains a lot of methods. Some of them are actually mutating the underlying data structure, and that's okay. But imagine you want to provide your own implementation that's actually mutable. So you create your own one, you implement, and you end up having a struggle with methods like add all, remove, or replace all. Because effectively, all that you can do is to throw an exception. And, well, that will work. That's kind of okay. But it at the same time violates Liskow's substitutional principle. Because new consumers of your API now need to be aware that potentially some of those methods can throw exceptions. So you might be tempted to an instance of check that if your list that you accepted is an instance of abstract immutable list, then actually get ready to process the exception. And this is not very handy. It turns out that the key to having immutable data structures that are actually easy to use and can be actually mutated means still providing mutating operations, but instead of throwing exceptions, you make them return a new version of your data structure containing the change you asked for. So if you have a list of one element, you want to add the other one. So if you call the method add, you don't throw an exception, you just derive a new value from the previous one. So the original list remains untouched, but the new one that you get actually contains the change you asked for. Just like with integers or other natural immutable values. But there is a problem with all of that. Because if you have a look at those implementations that I provided in kind of pseudocode, let's have a look at them. So we have 6 mutating methods, and pretty much all of them, the implementation start with copy with replaced, or something else. And that's quite a lot of copying, and quite a lot of iterating. So it turns out that we get immutability, which is the property we are after, but it turns out that at the same time, we lose most basic qualities of data structures that we want to work with. Because we judge our data structures based on the qualities like the time and space complexities that they provide. And if I'm working with an array list or a linked list, if I add an element, I expect this to be done in a constant time, and same with space. But if you add a new element to an immutable list, and internally you just create a copy of everything, it means it's no longer constant, it's linear. And that's not as good as we would hope for. Plus, if you copy so much, you generate quite a lot of garbage. And it turns out that this is the price that we pay for additional correctness guarantees that we get by implementing immutability. So if you jump into, let's say, Haskell and other languages, you will see that they actually create quite a lot of garbage. And that's okay, because in most cases, we don't care about the garbage, but we care more about the correctness guarantees that they give us. But still, could we do something better than that? Because, well, it's still very inefficient. And this is how we slowly arrive at the main topic of today, which is the persistent data structures, or some other call them purely functional data structures, or how I call them purely dysfunctional data structures. The way I call them, because is the ideas behind them, the design is really interesting, really cool, but it turns out that they represent quite a desperate attempt at making those things performant. So when it comes to persistent data structures, you might be thinking, oh, persistency, it means data structures that offload stuff to database or something. No, not really. The word persistent in this case comes from a different bounded context. In this case, it means that that those are data structures that are able to persist the previous versions of themselves. And we already discovered the first way of implementing such things, simply by introducing a brute force copying. If you have an immutable list and you want to make it persistent, you just, when you try to modify it, you just create a copy, and then you have two versions of the list living at the same time. But as you can see, it's very inefficient, so we are trying to look for something better. The other concept is an idea of a fat node, which is like in-memory event sourcing, where data structure would keep internally a whole log of actions that would actually request it, and use this to recreate every possible version of itself over time. That sounds really cool, but it's also one big memory leak effectively. Because if you keep a bin log in your data structure that records all the actions that happened, well, that will run out of memory at some point. You can, of course, apply a kind of custom retention mechanisms, but at the end of the day, that wouldn't be truly persistent after all. And this is how we arrive at structural sharing, which is effectively the most practical idea how to attempt implementing immutable data structures. Structural sharing, the idea is very easy. It's a bit harder to implement. So if you remember, what we said a few minutes ago is that the immutable data structures and any immutable values can be safely memoized and shared between threads everywhere. So because we know that the list containing one element, let's say the number 17, will always be a one element list with the number 17. So technically, by sharing those elements of data structures, we could arrive at something that's a bit more efficient. We could save some memory and obtain better time complexities from them. And this is the main trick behind that pretty much all languages use out there. And I'm not the first one to talk about the subject. I really like the talk delivered by Oleg Shalayev that's now working on the GraalVM team. In Devox in Poland, he spent an hour discovering, showing us those concepts. And the way I'm introducing this slide over there is that he illustrated those concepts with this cartoonish picture of a unicorn. And I truly believe that this image is scientifically incorrect. Because after playing around for some time with those data structures and functional concepts, I can agree that that's a unicorn, but the more realistic example looks like that. So yes, those ideas having about recursive immutable data structures that share data between themselves is really cool. But at the end of the day, they represent a desperate attempt at making those things, at least remotely efficient as mutable data structures at the same time. So we know now that string is actually a immutable data structure if we look only at the one certain abstraction layer. But is it a persistent data structure? So if you have a look at the implementation of the substring method from JDK8, you will see that actually, you know that internally the car array is actually immutable. So if we know the internal data structure used for storing, our car elements doesn't change over time, technically could be reused. And this was the case for some time. So if you did the substring method on a string, you could actually reuse the existing car array and just logically cap the string to make it appear shorter. And this was the case for some time. But guess what? There was a trade-off involved, because that would effectively create a memory leak. Because if the original string is no longer needed, the underlying car array would be actually still retained in memory. So after some time, they actually changed it. So the string class actually does the copy in the constructor. But let's say you could safely implement your own VM that actually does it this way. However, there's a slight complication if you try to apply the same idea to mutable data structures. And this is, for example, the case with the array list. Array list exposes a very similar method called sublist that allows to specify beginning and an end index. And then it actually returns a view over the original list without doing any form of copying. And it can be very damaging. We didn't have production issues, but we had serious test issues that actually would pass all the time because of that. Because if you access elements through the sublist returned by the sublist method, you don't operate on a new list. You still interact with the previous list because it's just a view over the original one. Imagine what kind of sneaky bugs can actually happen in there. Especially around Java 7, when we worked with Guava and transformers, they would also not create copies of collections. They would create views over original collections. If you composed a few layers of such views that mutate data over time and just logically cap your data structures, it's very easy to end up in a bit of hell when it comes to figuring out what's actually going on in there. Look, those problems don't exist if you work with immutable data structures, because you can just sleep just fine, because you know that no one will be doing any evil things underneath. So this is how we slowly arrive at the first implementation that I will show you today. It turns out that the purest form of the persistent data structure is a linked list that you know from, but it's not the same one that you know from university. It's a persistent singly linked list, which kind of still, at the end of the day, is just a collection of nodes pointing at themselves. But it's a form of recursive data structure. So internally, a list is composed of a single element and a pointer to the previous version of the list itself. And so imagine if you want to add a new element to such data structure, you just create a new instance, you add a new element and point to this version of the list. And this is very easy. It doesn't copy anything. It's constant time as well. So this is what we really wanted to from lists. And it's really cool. So if you want to kind of visualize this, imagine you start with a list of a few elements. You add one element, but you still point to the previous one. And then you add a few more elements. So those lists would point to the previous versions of the list, which would point to even older versions of the list. And this is how you can create a very simple persistent data structure by using this recursive pattern. But there is a trick involved, because as you can see, the prepend operation is great, because it's just very simple. You just create a new list, add new element, and point to the previous version. But what would happen if you wanted to implement the list append, which means adding from the other side of the list? It's not so easy anymore, right? Because there is no easy way to point to the previous versions of the list that doesn't really exist. And if you want to implement this, you need to recreate a new list starting with this new element as the beginning, as the first version of the list. And this is really sad, because we really wanted this constant time here. And it's no longer constant time, because you need to iterate a lot. You need to reiterate the whole list and still recreate some of the nodes in there. So, as you can see, we are already browsing the trade-off space. And you can imagine that once we start thinking about implementing trees, maps, it will get even worse. But more or less, this is quite okay, because at the end of the day, we are still thinking it's okay for lists. If we can fast add elements to one side, it's more or less okay. And this is how we slowly arrive at the main, one of the main things I'd like to remind you about the myth that immutable data structures are thread safe. Well, it's not really a myth, but let's say that haven't been told everything again. Because immutable data structures are great for thread safety. Of course, naturally, it's a great thing. But they are not always useful for multi-threaded scenarios. If you remember the story about the King Midas and the Golden Touch, he was really after this superpower of being able to turn everything into gold. And someday he got it. But then it turned out that the drinks, food, his family would change to gold as well. And I feel it's a kind of similar story with immutability and thread safety. Because yes, immutable data structures are thread safe if implemented correctly. But at the same time, they make it impossible to share updates through those, let's say, shared instances of those data structures. So I know some other ways of making Java, thread safe. We could remove, multi-threading, and well, you have a thread safe language, okay, because everything runs in one thread. Yeah, no, not so useful, right? So, so actually, if you really try to use immutability for concurrency, you need to, again, jump into some serious trade-off space. Because there are some ways to make it happen, but it involves quite a lot of concurrency, working with concurrency quite a lot. So let's say that we really, really want to use an immutable list for, let's say, storing, using it for exchanging data between threads. So we would need to sacrifice, we need to create one mutable field which would carry an immutable data structure. And this reference would be updated by multiple threads in a synchronized manner. And as you can see, we made it work with concurrency, but we were promised that we don't need to worry about concurrency, and we already need to write concurrent code and think about it. So this is not really cool. So we can either use immutability and try to apply it for concurrency and work with problems like this, not even mentioning performance issues with major contention, being focused on one single point. Or maybe it would just make sense to use a dedicated mutable concurrent friendly data structure, like concurrent hashmap or others. Think about this. Or maybe different ways of sharing updates. There's also a way to do that. And in order to make it a bit easier for you to imagine, that would be the same case, for example, if you wanted to share, let's say, a shared instance of a string and keep multiple threads appending data to it. At the end of the day, you would need to manually synchronize everything, and it kind of falls out. But some of you might know that there are lock-free techniques where you can kind of avoid, those huge major contention points when it comes to using a huge synchronized blocks. But again, it turns out that if you would have 1,000, let's say 1,000 threads trying to update one data structure at the same time, and you know that only one of them can succeed at the same time, so n-1 threads and n-1 objects would be the same time thrown at the garbage collector, causing some performance issues. So another trade-off and no clear solution. So with this optimistic, let's say, idea, let's move into a bit more tricky data structures to implement. So persistent set, we already know, that technically, we know one of the ideas how to implement persistent data structures by having this simple idea of a single linked list. We could use that for the set, and that would actually work. The problem with that is that, again, those data structures would exhibit patterns that are, performance patterns that are not okay for most of us, because we expect sets to perform in a certain way. Could we do something smarter than that? Notice that I said smarter and not necessarily better. It turns out we could use a tree. So internally, trees by themselves are data structures that are actually recursive. Any node of this tree could be actually a start of a subtree. So we can actually share some data while trying to implement a immutable data structure based on a tree. But we have some problems. Imagine that we want to add the value 42 to this list. We add it at the end, which means we need to actually copy quite a lot of things from the root till the end. And we can share only those black parts that are around that, 28 and 55. So again, we can't share everything. We can share just a small subset of the whole tree. Of course, it's a bit more efficient if you have big trees, because the bigger the tree, the more you can potentially share. But at the end of the day, we still need to copy more than we would love to. So, but the idea is pretty much the same as with the single linked list. So, could we now try to do something even harder, like a queue? It turns out we could use a list for this, but that would work really good as a stack, but not as a queue, which kind of has a different access pattern, where you add data from one side and take from the other. If we had a single linked list, that would be super inefficient, because one side would be adding or taking elements in constant time, and the other one, the consumer, the producer, would operate in linear time, which is really bad. It turns out that one of the tricky ideas how to implement a persistent queue is to actually involve a two persistent linked list. So if we know that a single one linked list is actually very good at adding elements from one side, but very bad at adding elements from the other, well, let's just put two lists together and form a queue. But those lists would be, one of them would be reversed, so that we can easily access the beginning and the end of those queues. The trick is, from time to time, we would run out of elements from one of them. So we would need to reverse it and rebalance the internal elements in such data structure. And it turns out that you can see it won't be always constant time. Most of them, mostly you would access them in constant time, but from the time to time you would need to do a linear time operation. So using some form of black math, you could prove that this is amortized constant time, that this cost of linear time reverse can be actually distributed over the common case, which is the constant time. But at the end of the day, you need to remember that that is mostly not acceptable for real-time systems, but still an improvement over what we had at the beginning. Could we do even something smarter than that? We could use a tree again. It turns out that we found the solution when it comes to building persistent queues. And it's based on a 2-3 finger tree. 2-3 tree is, just to remind you, is a tree which kind of keeps all the value nodes at the same level and has a variable branching factor from 2 to 3. And you might be thinking, Greg, but it's a tree, and if you want to access an element in a tree, it has some logarithms inside, and we want constant time. And this is all true. This is why they introduced a trick to easy access the beginning and the end of the queue. Imagine what would happen if you reorganize the tree and put the first and the last node into the root node itself. You would get something like that. And it turns out that this concept 2-3 finger tree works quite fine as a queue, at least on paper, because the idea is really noble, really nice, but it turns out that many languages actually adopt banker's queue as the main one. For example, Scala. And the banker's queue is this one with 2 linked lists put together inside. It turns out that this solution is still much more cache-friendly. So if you remember, the main difference when it comes to performance of linked list and array list is the memory layout of elements. And in linked lists, elements are laid out pretty much randomly in memory. And each jump between a node to node to node is a dereference, which involves effectively a cache miss, which makes it well, still some operations are constant time, but this constant time will be really, really slow. And if you go back here, you can see that not every node actually can carry a data. So while jumping from empty node to empty node to empty node, paying cache misses effectively for nothing. And this is why many languages actually go for the bunker's queue. And this is how we slowly arrive at the holy grail of functional programming, of the persistent data structures, which is the implementation of a persistent map. Of course, we know that there are very easy ways to do that. You could keep a list of entries, and that would be a valid base for a persistent map. But we expect, again, a different time complexities from such solution. And it turns out that there is a really clever idea how to solve that. And the trick is to use something called hash array mapped trie. And just to make it clear, the trie is not a typo. It's spelled T-R-I-E, because it's not a tree, it's a radix tree, which means effectively it's a state machine which kind of helps you represent prefixes of data internally. So if you store elements like T, TED, and 10, you can see that by using this data structure, you can quickly and easily navigate and find them by using their common prefixes. So imagine you are doing a Google search and you put a few words in there. And this kind of idea would be very efficient for solving this kind of problems. Google most likely is not using this, but they could, and that would work. So imagine we already have a tree-like structure that can store efficiently prefixes. The trick they use, they store hashes in a data structure like this one. And each hash code, they encode the hash code, they all have the same length, the binary length, and each part of the hash code points to a different node in a tree like this one. And the trick is that all those nodes, they use extremely high branching factors. For example, 32. So each of those nodes can hold even 32, children in themselves. And now we can pretty much effectively do lookups when it comes to particular elements. But again, some of you might note that, Greg, it's still a tree. It won't give us constant time lookups. And yes, it doesn't. But if we have the branching factor of 32, which is extremely high, imagine how many jumps we would need for the data structure that holds an integer of max value of elements. That's actually 6 or 7. So it's not constant time, but it's very close to being kind of a slow constant time, because you know that you will always need approximately around 6 jumps to get to do the element lookup. So yeah, it's logarithm of the base of 32, but it gives you a very predictable value out there. To give you a clue how slowly the function grows, if we do the same for the long of max value elements, that's 13, which is pretty good. There are, of course, many other optimizations out there. So, for example, Scala 2.13 is shipped with an improved compressed hash array mapped prefix tree. People started experimenting with concurrent-friendly and snapshotable versions of those data structures, ending up with something even more difficult. But in general, as you can see, there is a huge trade-off involved between when it comes to introducing immutability to your language or to your toolbox. But it's still worth it. So although I've been complaining here for almost 30 minutes about the state of them, it's still worth it, because they give you extremely good correctness guarantees. But at the end of the day, I want you to be aware that there is a price to be paid for that. If you want to give it a try, you have libraries like Waver, which is an ex-Java slang, or Cyclops to try out. I would encourage you to try Waver, because waiver is kind of borrows a lot of ideas from Scala directly. So if you're a Java developer going into waiver and then to Scala, your transition will be smoother. And if you are a Scala developer trying to work with Scala and with waiver, you will be less disappointed than working with core Java. So that's all for today. What I wanted to summarize quickly is that I wanted to show you that when it comes to designing immutable data structures, the key is to minimize copying and maximize structural sharing between instances. It also turns out that often when it comes to performance, the simple beats the complex one, just like with the case of a 2-3 finger tree. What I want you to remember that immutability is not a silver bullet. Think about it as another tool in your toolbox that has such qualities and pick it according to your context. I have no idea what your context is. So spend time, learn the tool, understand pros and cons, and apply in your context if you think it makes sense. Remember that trade-offs are everywhere. If you want to do a bit more reading, I prepared some white papers for you. The last one is especially interesting because it actually proves that having garbage collectors in your runtime actually can sometimes improve performance. And thank you very much. I hope you learned something.